This meeting is being recorded.
In section 4.3, we're going to take a look at constitutional isomers. You were introduced to this terminology with our first lab. We defined isomers. So those in general are different structures with the same molecular formula. And then we dived into a little deeper definition here with constitutional isomers. So they specifically have the same molecular formula, but a different connectivity of atoms. So what we see down here in with this example, these two structures would indeed have the same molecular formula, the same number of carbons, same number of hydrogens, but we can tell here that this carbon specifically, right, is connected to, in this structure, 2 carbons and 2 hydrogens, whereas in this second structure, it's connected to 3 carbons and 1 hydrogen. So even though the same amount of carbons and hydrogens exist, we would call these constitutional isomers because they have different connectivity of those atoms. So taking a look here in general of the number of possible isomers, we can see a trend here. So if we have only 3 carbons in our molecular formula, as we do with propane here, there's only one constitutional isomer possible. So minimal structures. So we would only see a couple structures possible for that chemical formula. But as we increase, so say to 10 carbons and 22 hydrogens with this alkane, we could have up to 75 possible constitutional isomers. So we see kind of this exponential increase as we increase the number of carbon atoms. But you will not be responsible for that many isomers ever. So maybe up to something like this with 6 carbons, you may see on an exam. And again, we practiced some of this with our first lab. So you may recall in those post-lab questions, you were asked to identify whether something, oh, sorry, we lost track here. So you were asked to identify whether something was an identical structure or whether it was a constitutional isomer. Let me find my spot here. Where were we? Here we go. So back to how we can determine if this is the same structure or an isomer. So that previous chemical formula that we saw, C4H14 here, or I'm sorry, C6H14 from this slide here, that's what we have generated the isomers for down here. So we have, right, C6H14 here. We have our second isomer. We have a third, a fourth, a fifth isomer, right? Back from this slide, we see there's 5 possible. And then we draw this structure here, and we want to confirm that it is a separate structure and not an identical structure to something that we've drawn before. So there are 2 ways to do this. So the first is to see if there are any carbon-carbon single bonds that we could flip or rotate in 3D space so we could make, in this case, these 2 molecules superimposable. So yes, if we rotate around this carbon-carbon bond here between 1, 2, 3, 4, between carbon 3 and 4, we would generate this structure here, right? So we have 1, 2, 3, 4, like that, right? If we rotated that, that bond between carbon 3 and 4. The second way to identify if it's an identical structure or isomer is to name the compound. Same IUPAC name would mean that they are identical. Identical. So if they are named the same, they're the same compound. So let's take a look at our 2 structures in question, and we'll systematically name that. So again, if we performed that 180 bond rotation, right, on between carbons 3 and 4, we would generate this structure here. So let's name it. So we number our carbons 1 through 5. We see at carbon 3, we have a methyl group, so we have 3-methylpentane. let's name this structure as well. So we number our longest carbon chain, 1, 2, 3, 4, 5. So we also have pentane, and then at carbon 3, we have a methyl substituent again. So since these two compounds have the same name, they would be identical, and they would not be considered different isomers.